technologies in a quantum realm. So I know that in class 11 people usually do not study quantum mechanics well. So, so in other words, I will be talking about quantum technologies. So I will actually discuss some of the inventions of quantum technologies. Try to convince you in next 40 minutes or so that why we want to build quantum technologies and try to tell you that they are more efficient than the one that we are using nowadays. So when we think about technologies, then the first thing that came to your mind is possibly computer that the students use quite often. And then the technologies like communication technologies, the devices that we use are, for example, mobile phones, internet, how we connect each other with friends, with relatives, and so on. At the same time, they are also useful, for example, to do, say, internet banking, mobile banking, etc. At the same time, we also use other kinds of technologies like refrigerators to store food. And when we use, say, desktop or laptop or mobile phone, another things which play an important role are batteries, where we store energy. And even when there is no electric connection, then still we can run it. So when we buy mobile phones, we usually take care that whether they can stay longer without charging. Right? So these are the useful technologies that we use, and they are integral parts of our life. Now, what I will try to tell you that actually we want to build something, the quantum version of it, like quantum computer, quantum communication, and say quantum devices like refrigerators, batteries, etc. Now the question actually we will try to answer today, why we want to build, because we are very happy with the technologies that we are using. For example, the laptops that I am using to present this talk, or the mobile phones, the batteries that we use, and so on. So the main aim today to convince you in the next 40 minutes or so that why we want to build quantum technologies. So let's start with why we want to build or devise quantum computer. So the computer that we use, say desktop, laptop, and so on, these I call classical computer because they are built based on classical mechanics, classical electrodynamics, classical information theory. So individual desktops are quite efficient, that we know from our experience. At the same time, too, when many computers are together, attached together, which we call workstation, they also can perform certain tasks which are much more efficient than an individual computer. They are more powerful in that sense. So the computer, now we know the applications, it has applications from education to health, medical purpose, in government sector, in banking, even in entertainment, right? So there are a variety of usefulness. At the same time, this computer are also useful to solve certain mathematical problems. Okay? I will talk about that problems. So before I go to that, let's talk that the basic unit in which the classical computer works are bits. It's one of the zeros and one. So they are distinguishable. Why I am telling distinguishable will come in this talk. So typically we give the input to a computer which translates in some zeros and ones, so strings of zeros and ones. Then there are some logical gates which manipulate the zeros and ones. And finally we get output which is again in bits. basic kind of steps that is followed in a computer, which I call again classical computer. Now let's discuss about a problem. Okay? So suppose I give you a number and I want to know whether a number is prime or not. So even in class, I think 3 or 4 or even later, you actually know most of the prime numbers, say up to 100. If you go on, you can go up to 1000 and so on. But suppose I give you this 10-digit number and you have to tell me whether a number is prime or not, then you have to check systematically whether you get the number. Actually, I will type these numbers just randomly. And then I found that it is, so first thing I only took care that the last digit is odd, so that there is a possibility that it turns out to be prime, but if it's not, you can check that this is actually divisible by 7. Okay? So what I wanted to tell is the following. Like, can we design a program or algorithm by which I can solve any n-digit number in a reasonable time? I will come in a minute. Is it working? No. Hello? Yeah. Hello? Yeah. Okay, so the point is reasonable time means, suppose I give you a 10-digit number, you write a program. And if I give you a 100-digit number, I also want the answer whether a number is prime or not in, say, in few days or in few minutes. I don't want to wait, say, 100 years to find the answer, right? So that is what I mean by reasonable time. It actually has some mathematical way to express. So till 2002, although this looks a very simple problem, right? I give you a number, you have to tell me whether a number is prime or not, and that we do in class 3, 4 or something, right? And so you can think that this is a very easy problem, but it was unsolved for quite a long time, when these 3 computer scientists from IIT Kanpur, they solved this. So what they find is the following, that they found an algorithm by which you can tell whether a number is prime or composite within a polynomial time. And this polynomial time, which I kind of naively was telling about the reasonable time. What do I mean by polynomial time? That if I want to solve an n-digit number, then this should be order of n to the power alpha, say n square, square root of n, and so on. Okay? So this was done by these people. So this is a good news that we can solve it in polynomial time. Now the second problem. So this is finding a prime factor of an integer. So I give you an integer, say for example 45, and you have to tell me the prime factors of it. So if I give say 45, we know immediately. Okay? I tell you 72, you know. Now I give you 35-digit number. Okay? So then again, you have to have a proper algorithm to find out the prime factors of it. Okay. Actually, the known algorithms which you can do in a classical computer, you can check that this actually requires that many steps to find out an arbitrary 35-digit number, whether the prime factors of 35-digit number. This actually we did with my one of my old students from Udna. So, and in a reasonable computer, actually it takes around 120 seconds. So, it actually goes on. So, if you have 82-digit number, then the known algorithm takes almost 1.1 year to give the answer. And if it's just 120, it will take this many years and so on. So as you see that with the increase of number of digits, a known classical algorithm, that is a known algorithm that you can use in a normal computer, as powerful computer as available nowadays, say a supercomputer, the time scales exponentially. So, very precisely speaking, to factor an n-digit number, a known algorithm in a computer takes this exponentially n steps. And you can check that it will be, the time also increases exponentially when you increase the number of digits. So there is no efficient classical algorithm known till then. So now the quantum mechanics plays a role, and in 1994 it was discovered by Peter Shaw, US mathematician and computer scientist, that quantum mechanics can solve this problem, this prime factorization problem, in polynomial time. So if I just compare, then classically this is the time axis and this is the number of digits, and you see that classically just increases with the number of digits exponentially. On the other hand, quantum mechanical, it takes polynomial time. So this is a kind of breakthrough where people are more or less convinced that one has to build a quantum computer because it can solve certain mathematical problems much more efficient way than the classical computers that we are using nowadays. So this is Peter Shaw. Now, around this time and later on, there are several algorithms discovered where it was shown that the quantum mechanics help to reduce steps in solving any mathematical problem. So, Roberts, George Johnson, these are very prominent ones, but there are many. So, up to now I have just used quantum mechanics. So, of course, it's very hard to tell about quantum mechanics because I also do not understand them. So, let's try that what we want. So, quantum physics describes actually microscopic particles. So, macroscopic particles are those particles like a football or like this desk, table, chair, which are huge. On the other hand, quantum physics describes small particles like atomic, subatomic levels. So it was around a century back, around 1920s, Einstein, Schrödinger, Heisenberg, you can try to see whether you know all of them, all the pictures. And also the Indian contribution like Satyendra Bose and others were contributed enormously to formulate quantum mechanics, which we now learn or study in typically in BSc, MSc, and so on. Here I must mention that these etals are important since I am a theoretical physicist. Possibly I put all the names who do theoretical physics, but there are very important scientists like this, especially experimentalists, which play an important role in formulation. So, just actually already you got a kind of ideas from the last quarter of complex samples. So, it's much easier for me. So, in quantum mechanics, if I have a situations to describe in a physical system, I describe this is associated with the vectors in a linear space where an angle defined. And this is actually called formally a Hilbert space. And we will be talking about a two-dimensional complex Hilbert space. And if I want to represent spin of an electron, I'm not going into detail, but you know what is electron, proton, neutron, and so on. So there are something spin of an electron that can be represented by a two-dimensional complex Hilbert space. And that actually helps us to get the basic units of quantum computing. So basic units of a classical computer we have already discussed, that is bits, one of zeros and one. Now similarly, we can have a basic unit in a quantum computer which is called qubit, and that is quantum bit. So what is that? So it's actually an arbitrary two-dimensional quantum state. Now I haven't defined what is quantum state. So this quantum bit you can define by using the principles in quantum mechanics called superposition principle. So, very nicely, it's a story of a cat actually. So, in classical world, you see a live cat as well as you can see dead cat, right? But quantum mechanics tells us that we can have alive plus dead cat at the same time. Okay? And that leads to a superposition of quantum states. And that leads to actually the quantum bit, which is a basic unit of quantum computing. So, if I talk bits, what is quantum bits in terms of geometrically? So, if you have a sphere, just say a ball, then the north pole and south pole represent two distinguishable objects. Okay, so that I call say 0 and 1. Now the surface of the sphere, there are infinite number of points, right? In a sphere, if I talk about the surface, right? And this surface of the sphere, all of them represent quantum bits. Okay. So just like a classical computer, you have universal classical gates, possibly you people know that. And in quantum computer, there are also universal quantum gates. I'm not going into detail, but if we build a quantum computer, then the manipulation, just like classical computer, bits are manipulated by classical gates, the universal gates. We also have a input like quantum bits. Then the manipulations will happen by using universal quantum bits. So it's not only theoretical prediction, it is experimentally, it is possible to, up to now, it is possible to build a small scale quantum computer. So by using different quantum mechanical systems, this is with track patterns, with 11 qubit, but there is something probably you have seen the news where there is something called quantum supremacy. So it's a Google who claims that they built a 53 qubit quantum computer which can solve certain problem in 3 minutes 20 seconds, and they say that the best classical computer available in the world, a classical supercomputer, actually requires 10,000 years to solve that task. There was a lot of controversy because after this results published in Nature in 2019, IBM showed that this is not the case. Actually, you don't get exponential speed up, the problem of the task they have chosen. So, and also recently, Chinese group have shown that to solve this task, you require only 5 days in a classical computer. And in quantum computer, it's still 3 minutes, 20 seconds. So, you get, of course, speed up, but not exponential. So, the problem that I have told already, this prime factorization problem, here really you get exponential speed up. That actually to show that the quantum computer gives exponential speed up, you require to build a quantum computer of certainly around 1000 qubits, which still people are not able to build. Okay? So this is kind of timeline that they published and how for the next 15, 20 years they are trying to build. And there are several companies that you know, say Google, IBM, Microsoft, they're all trying to build quantum computing. And there are many startup companies, including many in India, they are trying to build quantum computer. A lot of research going on. So today in the morning you have heard that there are, to do a basic science research, now also you can go to industry to do this kind of research. There are a lot of startups coming up even in India where they do research on quantum computation. If you are interested, you can Google it, you can find in IBM, there is something called Qiskit and so on. So you can look. I just want to emphasize one thing. So making a good lantern or a candle doesn't lead to a LED bulb or a bulb. This is really revolution in technology. Similarly, making a very good classical computer doesn't lead to a quantum computer because this is a computer like qubits. Because suppose I want to build a quantum computer, then inside the circuit I want to send some information. That I will do by, say, quantum state transfer. So there are two possibilities. And so one can show that actually if you make quantum versions of the communication protocol, they provide better efficiency in most of the situations. And so for example, so they are known as something called dense coding teleportations I'm not discussing. So I just want to give you some essence. So suppose Alice wants to send some qubit quantum state to Bob. He factor down from the black ones. Right? And these are the unentangled states. Now you can have much more. So here there are more things. But again, you can see the first line can be factored out. Here x, y are complex numbers. Okay? So these are the unentangled states or the useless bridge. So if Alice and Bob to share entangled states. So this is the typical way to make a quantum bridge. And this, if Alice and Bob share this quantum bridge, then they can do some communication tasks which will be more efficient than the classical known protocols. It looks a nice story, but there are several open problems, and probably that will interest students because if some of you come to basic research, then you see also in industry, so people are trying because if experimentalists give us a quantum state, finding whether a state is entangled or not is an open problem kind of, so it's not always possible. So there are a lot of scopes to do research in this area. So finally, since here we in our communication protocol that we are now using, all are connected, right? Somehow. So if you go to LinkedIn, you'll see whether you are connected 3 or something like 4. So somehow you know the connection. So we want to build something like this kind of network, but we want to do a quantum version of it. This is the aim. And this is one of the biggest challenge in this field. So people, because you have to make that many quantum bridge between so many people, which is not easy. And so we work on that at HRI, for example. Recently we proposed some method to make this kind of bridge in different scenarios. So there are a lot of experimental achievements. So if you think about photons, so for example this light which is kind of bothering my eyes, there are individual particles of lights that are actually photons, right? So if you use these photons, they are a good, they are good quantum system to do this communication task. And for example, there was a breakthrough experiment in 2017 where they are able to perform the teleportations that I have very briefly discussed between two cities which are 1200 kilometers away. So this is led by Professor Pan, and previously the known record was around 100 kilometers, and now it is possible to connect between two cities which are 1200 kilometers away. So you can think that we can now connect Guwahati, Kolkata, or Mumbai, Chennai, and so on. So this quantum communication protocol is possible among this distance. And we also work on these directions of how to really make a network in this by using photons. So last 5 minutes I have. Yeah, so then I will talk about with security. So up to now, the communication protocol that I have discussed, I haven't used the word security. I just was talking that Alice wants to send some information which can be whether of say the Allahabad or the water level of Ganges, etc. So this is kind of, suppose I want to send that information to the newspaper editor. So this is a classical information sending, and there is nothing secrecy on that. So now let's discuss about the quantum communication protocol with security, which in other words is quantum cryptography. So again the questions, why we want to build. So this secure communication means one wants to send some classical information secure. So up to now we were just talking about Addison block. Now there is a eavesdropper in between. Okay? So Alice's task is to encode information in such a way that no third party can gather that information. On the other hand, eavesdropper idea is to gather as much information as possible that Alice is sending to Bob. Okay? So we have to somehow optimize between the Eve's power and the encoding power that Alice of the center has. And this is extremely important because possibly even in COVID era we realize that how important not going to the bank but to internet banking and not going to the shop just to buy things from Flipkart or Amazon, right? So in all these cases we have to do a money transaction and that has to be done very securely. And I think whenever you do suppose you are kind of setting password, you always get that kind of information that put uppercase, put the number, put hash, something and so on. So why they are doing? Because they want or we want certain key, that is the key or the password to be used, which should not be hacked by someone, right? So this secure communication is now integral part of our life. At the same time, the secure communication is important for national security of any country. And that we realize from ancient times. You probably have heard the story of World War II where they used cryptographic system which was kind of broken and so on and so on. So in all these current secure communications are quite secure because we are happy with our internet banking. I hope we all are sitting and we are thinking our bank account is safe, right? So it's safe. Okay. So the security is in all these cryptographic systems. Security is based on the belief that the mathematical problems cannot be solved in a classical computer in polynomial time. And the mathematical problem means the factorization that I have discussed. Okay? Now you see the problem because suppose eavesdropper has built quantum computer, then all our systems are insecure. So don't rush because no one has quantum computer, so still we are secure. Okay? So what is the remedy? Again, remedy is the quantum mechanics. Based on quantum mechanics, so if you believe that the quantum mechanics is valid, then based on that, you can propose a quantum cryptographic system which will be secure even when you have a quantum computer in the market. Okay? And this was proposed by David Bachelor and Descartes in 1984-91. So this is Bennett. This is Russell and Descartes. And Bennett, this picture was taken when he was actually visiting Gujarat. So here, to generate random key, we use quantum states. Okay? Instead of sending classical bits, quantum states are sent randomly to generate keys. An important point is that quantum mechanics ensures that even if there is an eavesdropper in the channel, we can detect it. So this is the big good news because the quantum mechanical principles tells us that presence of eavesdropper can be detected. So it seems that this is the end of the story. It's not because there are a lot of open questions here because the security depends on what kind of attacks eavesdroppers are doing and whether we are we can protect our encoding system and so on. So there are a lot of wars going on. There are many companies who are working on that. And it's also not only theory, because this cryptographic, quantum cryptography is very well advanced subject. So in 2001, there was a quantum cryptography was demonstrated, say between around 70 kilometers in the Geneva Lake, between Geneva and Ozone. And later on, it was even used in the football World Cup in South Africa. So they want to send some information secretly in where they want to send some message outside the stadium. There was a use of even a Geneva election they have used. There are several examples. Okay, so these two experiments that I have discussed were done led by Professor Gizo, which is a very well-known scientist in the field of quantum cryptography. So we also worked on that. I'm not going into detail, but I just wanted to tell that there are several open problems here also, where the basic principles are kind of established that quantum mechanics can give you some security, and even when there is a quantum computers, quantum cryptography cannot be broken. But there are several loopholes, as I have already said. So there are several possibilities to research. So I just want to finish with the saying that there are India's effort also to on building quantum technology. Department of Science and Technology has launched a program called Quantum Enabled Science and Technology. There are many directions where the research are going on. We are part, HRA faculties are part of this and so on. So there are almost like 53 experimentalists and theorists work together to build different kinds of quantum technology. And I think this was the news probably many of you heard, because there are some around 8,000 crore were declared where in budget 2020, where they said that this is a national mission for quantum technology. So I think I'm kind of able to convince you, I hope. So we are heading towards new era. So quantum mechanics can revolutionize computation and communication capabilities that we have with and without security. So as I said, quantum cryptographic system is already a reality. Possibly we are trying towards building quantum communication network, which I call quantum internet, by which we connect. Hopefully we meet next time when we do exchange information via quantum something, and we all have quantum mobile with hand, and or some of you will build and we will use, and towards quantum computer finally. So this is my group here. Some of the works that I have presented were done by my students, postdoc, and master students. This is the QIC group at HRI. So there are group leaders, Arun Kumarpati, Ujjwal Sen, Devdas, and myself. And this is the entire group. It's an old picture. Due to COVID, we are not able to take a new picture. We hope there will be an occasion. So there are 22 PhD students. We have 4 faculty members and 4 postdocs and many project students working. Many of them actually also from Allahabad. So thank you very much for your attention. Yeah.
Please ask. And using quantum mechanics speed up the technology, speed up the process, or other advantages.
Sorry, can you speed up the process?
You might speed up the technology, speed up the process. If there's other advantage of this technology.
So maybe he's asking that you describe that the process is accelerated, but are there other advantages?
Okay. Yeah, there are other. Actually, I have just discussed, for example, consequence in cryptography as we somehow make the loop complete at the end. And there are also other things which I haven't said, because this development also help us to understand quantum mechanics, so the fundamental questions of quantum mechanics in a better way. This also is important to build quantum simulator, like the old question by Feynman, where he asked that whether the classical many-body problems, if you can solve in a classical, or quantum many-body problem, can you solve in a classical computer or not? So we understand more about the directions. People can build quantum simulator where they can solve many body problems. So, for example, something called lowest eigen energies of a chemical system and so on. So there are other things as well. If I understand your question correctly.
Dr. and some technologies. And in previous slides, we have seen that quantum technologies are very fast. So, ma'am, why these technologies are very fast in comparison to our existing technologies?
Because of this superposition principle. Because of the basic thing is that, as you see that in classical world, you have always a distinguishable objects. Like the color of our shirts, right? We can understand that you're this red, then there is a brown checks, pink, blue, and have objects which are not distinguishable. And that gives the power of quantum mechanics, and that is the main pillar or main base to build quantum mechanics, which are not, which do not exist in our classical world. I mean, sometimes we cannot distinguish colors, right? But that's the deficiency.
Quantum mechanics. Now, is it possible that we can communicate through galaxies? Like if there is someone else on the other end which is also trying to connect to us, is it possible like that?
Actually, the connection that I showed, 1200 kilometers. Okay, so there are many issues. I cannot answer at this point, but what I can say that is actually satellite based. So in this 1200 kilometers, because we have to share the quantum bridge, the entangled state. Now you know the name. So how to build this quantum bridge between 1200 kilometers? So what they did, that the satellite which is there, they create the entangled state, so they have the machinery there. Then they send one particle to one of the city, say Allahabad, another in Delhi, and then they communicate. So
there's a sender and there's a receiver.
yeah.
So there could be a receiver out there and we can send the signals.
Yeah, so there are issues, other experimental issues, but in principle, wherever quantum mechanics is valid,